today on the new developments in the MNE software. So Richard is a research engineer working at INRIA, but also in close collaboration with Neurospin, with Sophie and Virginie on the MEG side, and also Maximilien Chaumont at ICM. So Richard is paid on an INR open science grant in collaboration between INRIA, Neurospin, and ICM on some of the topics related to I would say bids and standardizing the pipelines for processing MEG data, and he will show some of this today in complement also with other efforts that have been done by the MNE team over the last, let's say, couple of years. So Richard, the floor is yours. And
Thank
so
you.
I forgot to say what Florent told me, which is that the talk will be recorded, including the questions. All right, now the floor is yours.
Okay, thank you, Alex. Bonjour, good morning, everyone. And I think I jump right in. I suppose most of you actually already know what MNE is. For those who don't know, it's a free and open source software which helps you analyze and process your MEG, EEG, and other electrophysiological data. It's developed by a large community. Like I said, it's a free and open source project. It's hosted on GitHub. Anyone, at least in theory, anyone can contribute, can add new features, can report and fix bugs. And this list here of contributors is just, that's I think only a fraction. I think in total there's more than, last time I checked, more than 200 or so individual contributors so far. So many people have contributed. Some of them only once, lots of them multiple times. Meaning MNE is truly a team effort. This is just a screenshot of our GitHub website. And you can you actually see my mouse cursor? Can you see that?
Yes, we do.
You can, okay. And as you can see, we have, we're slowly approaching 1,000 stars, which means the project is kind of popular. And there is over 570 forks so far. Fork is a person decided to create a copy of the repository and work on it on their own. So there is a vast interest into this software. Because there are so many collaborators and because there's so many different topics people are working on, doing research on, our change logs often are quite big. And I want to show you what it looks like and probably feels like scrolling through a changelog of a recent version of MNE. So that's just for a single release, okay? And it's quite long. It's actually so long that I assume that most of the people attending here, most MNE users never read the full thing. And this is precisely why we decided to have this small presentation today to show you what have we added in recent times, what are we up to, what are we planning to implement next. I will do something that one normally shouldn't do, at least I have been told so, which is showing you a live demo of one feature which I think is probably the coolest we have added in recent times. Just takes a second to pop up. It's the 3D visualization of source estimates. It's an interactive plot. I can click here. I can rotate the brain. I can zoom in and out. I can adjust the color scaling like this. I can click on a certain region, on a certain voxel, and I get the traces of activation over time down here. I could even use an atlas and select a specific region of the brain, for example, right here. And I can see the activation of this entire region down here in the trace. By default, it extracts the mean signal of that region. I could also opt to have the maximum displayed here. And it's super nice. So currently, I'm looking at 2 hemispheres. I could also look only at the left, for example. Always takes a few seconds to start up. Now this is just the left hemisphere. And now there is a cool thing, which is this play button. And if I press this play button, we can see how activation changes over time. And I think that's really awesome. So far, we've only looked at the inflated cortical surface. Maybe I want to have a different view, different visualization. So this is not inflated here. Might be more difficult to see the sources, but it's all possible and fully interactive. Okay, end of the live demo. Let's go back to the presentation. Now, there was always a desire to embed this functionality into a Jupyter notebook that can run on a remote server. And thanks to Guillaume Favillier, who has, I think, almost like 99% of all that 3D development has been done by Guillaume Favillier. And he took on the task to add this feature to notebooks. And this is just a small demonstration of what it can look like. So you get the 3D visualization right inside of your Jupyter notebook. You can interact with it. You can adjust color scales. You can pick individual vertices. And this is just the visualization of the co-registration, meaning the sensors in relation to the head. So that is super cool because it allows you to provision an MNE installation on one central computer, one central server, and your users would just have to use a web browser to connect, and they would immediately be able to use MNE and to do the 3D visualization stuff without having to install anything on their computer. At least that's the theory. And I think that's super cool. Let's move on to some other features we've recently added. As some of you may know, we have a feature that allows you to annotate raw data. So if you have, for example, different conditions or maybe segments in your data that are problematic, where the sensors produce noise or were completely flat, you want to mark them, maybe you want to exclude them from processing. If you make good and extensive use of these so-called annotations, you might end up with data where there's so many annotations that it's difficult to see what is going on. And for that reason, Daniel McCloy recently added checkboxes that allow you to toggle the visibility of individual annotations, making it easier to explore your raw data. So I'm coming from EEG. My background is in EEG. And there it's super common to use ICA for artifact correction. I know that some of you also do it for MEG. That's why I'm bringing this up here. And this is what the MEG class looked like. You wanted to create that with an earlier version of MNE. There were multiple parameters that seemed kind of related. The names were kind of similar, and everybody was confused. What the heck is the difference there? And it was not only users who were confused, but also developers. We had endless discussions, and finally, yeah, this is what we all felt like. And finally, we cut this down. Now there is only a single argument which specifies how many components would you like to generate or would you like to extract, and that's it. Making ICA so much easier and covering still, I would say, 95% of the use cases of the common users. This is another cool feature. We have improved the interactivity of the ICA plots. So this is a plot of the ICA components that were discovered in some sample data. And you can see here, for example, ICA component 001. This kind of seems like a heartbeat, but maybe to be sure, we want to inspect some properties of this ICA component. And previously, we would have to switch to the Python command line and enter a command. But now we can just right-click on the component name, and we get this property view right there. And we can inspect and decide whether we would like to mark this component as bad, mark it for rejection, or whether we would like to keep it. That's super cool. This is the result of an automated independent component detection that tried to extract components, to isolate components that were most likely related to ECG activity. And I'm just presenting this here because there have been improvements in how this extraction actually works. I don't want to go into details, but essentially it's a pattern matching and some thresholding is involved. And previously you had to set the threshold manually, but now there's also an auto setting which automatically tries to find a suitable threshold to extract your ECG components automatically. Also, we have added functionality to automatically detect muscle artifacts. This is based on a Z-score procedure, and it creates these annotations in your raw data, which will be excluded from further processing. One feature that has entered the development branch, I think yesterday or the day before yesterday, so it's super new, is the describe method for raw data. You get a nice summary table of the channel names, the types, which units are being displayed, and the minimum, maximum, median, and the first and the third quartile of the signal, which can help isolate channels that might be, well, a bit problematic. Generates a nice overview, I believe. You can also, this is essentially a pandas data frame, which means you can also easily export it into a CSV file or an Excel file and store it with your analysis documentation. One thing that caused confusion in the past is that if you had baseline corrected epochs and later on decided to crop the entire or part of the baseline and then looked at the cropped epochs again, MNE would tell you, hey, there is no baseline. Baseline is turned off, which of course is not entirely true. I mean, the baseline, it would mean actually that the baseline period was gone, but the baseline correction hasn't been undone. Now we report the baseline that has initially been used for baseline correction, and we just say, hey, the baseline period was cropped after baseline correction to be less ambiguous. So I think that's that reduces lots of confusion. We have been working on a tool called MNE Bits. MNE Bits is a Python package that builds upon MNE and allows you to read and write bits data. Bits, for those of you who have never heard of that, it's the brain imaging data structure. And it essentially specifies a way to name your files and folders and how to build your folder structure. So if you look at this picture on the left, this is maybe the data you might have collected in your lab. And this is kind of arbitrary. So say you create a processing script which expects the data to be in this format because that's what you use in your lab or in your work group. And then you share this script with a collaborator who works in a different lab. They usually won't be able to use the script because their data structures are just different. The files are named differently. The storage places are different. And Bits is supposed to do away with that. It specifies a subject, or data for a specific subject is to be stored in a subject name directory, etc. And it specifies how each file has to be named. And MNE Bits really just leverages MNE Python to interact with these data. I think Sophie Herbst will talk in detail about this in 2 weeks or so, if I'm not mistaken. So I won't go into details here. I just wanted to mention that this project exists and there have been great advances in the past months. I just want to point out one nice feature. It's still in an early stage, but we thought, since the data you have is nicely specified according to bits, wouldn't it be nice if you could maybe auto-generate your methods paragraph or part of your methods paragraph of your next Nature paper? And this is the result. So we have this function which is called make reports. And it generates an abstract which says, okay, there were so and so many participants in the data. We conducted the following recordings, MEG or EEG or whatever, and the following filters were applied. And I think, so, like I said, it's still in early stage. It's a toy at this time, but it might develop into something more useful in the future. Back to MNE. There has been, so officially the MNE logo, I think it says MEG and EEG processing and visualization or something in that, of that matter, but it focuses on MEG and EEG. But this is actually not true anymore because MNE now supports many more types of data. For example, functional near-infrared recordings or intracranial recordings can be visualized, can be processed with MNE. I think the functional near-infrared is still in quite an early stage, but it's already usable. And the ECOG support has been in MNE for a bit longer, if I'm not mistaken, and is a bit more mature. So if you have data like these, you might, maybe you should feel inclined to try to process them with MNE as well. It can do that. and you get these nice visualizations. I think they're awesome. Now, this is a bit of my baby. It builds on MNE bits. So you can see how there is these chains of dependencies, right? So MNE itself, it depends on so many packages in the Python scientific software stack. Then there's MNE bits, which builds upon MNE. And now there is this thing which we call the MNE study template, which builds upon MNE bits and MNE again. Actually, I might as well show you the website because I think it looks quite nice, so I want to show it. Around. So the MNE study template is essentially if you will, a collection of scripts that you can use to process your raw data entirely. So it's an entire processing pipeline. You start with your raw data. It has pre-processing steps. It epochs your data, and it even does the source localization, and in the end creates an extensive report that you can share with your collaborators. Essentially, so here we have a gallery of different examples. This is a data set, the localizer data set. This is the data that was recorded here, or the paradigm was supposed to be a visual motion localizer. And this is actually data that has been recorded at Neurospin. So therefore, we were eager to see how the study template could perform on that. And as you can see here, there's a list of functionality that we have currently implemented and that we're using with that data set. And down here, we can see the generated output. And let's just maybe click on the ICA results. Here, you can see there are still lots of small details to fix. There's a bit of overlap here. But what you see here is the automated ECG artifact detection. And this is the signal in red. This is the signal before ECG artifact correction. And in black, it's after artifact correction. So this was processed entirely automatically. Looking at the end results, this is just a single participant here. We can see that we do get an evoked field. So it looks cool. We get an overview over the topo maps. Here, there's a bit of redundancy in the figures. Here we have GFPs. We can compare different conditions, and we get an overview over the filters we applied, and maybe there were bad channels. There aren't any bad channels here anymore, but we can see which EOG and ECG channels were used. So this is the kind of report you can generate. Oh yeah, this is also worth noting. We have a procedure for an automated scoring of channel signal quality. And you can see the scores on the left side here in red. The darker the color, the worse the signal quality of that specific segment. And on the right side, you can see if a certain limit you can set was exceeded. And if a limit is exceeded for a specific number of times, the entire channel can be marked as bad. Here we get an overview of the events that were found in the data, which I think is also quite helpful to get a better impression of whether the data was actually read and processed as intended. I can maybe also show you the averaged report, because here, so like I said, for this example, we only processed a single subject, but you can already see here that we get a summary of the numbers of different conditions that were in this data set. So this again helps you to figure out whether everything went as expected, or maybe there was a problem with the triggers or whatever. Okay, let me switch back to the presentation. So this is the data set I just showed you, or one file, one subject of the data set we processed, which I just showed you. Oh yeah, and the data set has been made available on OpenNeuro, which is a platform for sharing bits formatted data. So we took the data, we piped it through MNE bits, made it bits compatible, and published it on OpenNeuro. And then you can download it and run the pipeline. On the right side here, you can see the configuration file I used to tell the pipeline what to do. So it's actually quite simple. It's just a Python file, and it really just looks like a text file right here. And you can see the first 20 something lines. I think in total it has 40 lines, including comments. So you specify which subjects to process. You can specify whether it should try to detect problematic channels. Do you want Maxwell filter? Do you want a frequency filter? Would you like to resample the data? Want to do ICA or SSP, etc. So that's quite neat. Oh, I already showed you that. This is also something that the study template does automatically for you. This is now based on a different data set. And that's the results of decoding. So you can just say, hey, I have two conditions in my data. So you have an evoked study, okay? And you have two conditions. And you want to see, is there a difference between the brain response to these two conditions? And you just specify the two condition names and tell the study template, hey, calculate the contrast of these and do some decoding, and it would automatically do a time by time decoding using logistic regression. And you would get a result that hopefully looks like this. I mean, that's an amazing, these are amazing scores. And also, when possible, we also try to do source localization. We haven't implemented this yet for the localizer data set I showed you earlier, but this is for an example data set. And you get a plot that looks like this. As you can see, we still have to optimize a bit the usage of the space. There's lots of white space or black space for that matter. But in general, you can get all of that inside the report that the study template generates for you automatically. Also, we embed images of the boundary element model, and you can actually interactively scroll through the MR images and see if the edges of the model actually make sense, just as a sanity check. So that's quite cool. And it's really, it's compiled into a single HTML file. And this makes it very easy to share. Super nice feature. So this was all based, what I showed you so far was all based on MEG data or simultaneous MEG and EEG recordings. Now, there's a data set called ERP Core, which has been published by Steve Luck. Maybe this name rings a bell for some of you, and Emily Kapperman. And the idea there was to have recordings, clean recordings, following best practices of some paradigms that elicit commonly known, widely used evoked responses. The idea is that you could use these data and could essentially verify that your processing pipeline generates the expected results. And that's what we also did with the study template. And this is just an example for, oh, I think that's for a P3. Yes, I think that's for an auditory oddball paradigm, if I'm not mistaken. And we expect to see a P3, and in fact, we do. So it works, and I had to do a few adjustments to make the study template work with the specifics of EEG. For example, in some analysis, they would want to restrict the processing to only one electrode, and maybe you want to merge different electrodes. For example, they had two HEUG electrodes, and I had to turn this into a single HEUG and stuff like that. So on all these features I have just recently added, and it works. And I will soon add this to our example gallery on the study template website as well. So now with all these super cool features, sometimes you might run into issues, because I mean, MNE is complex, it's ever changing for the better, but some things are still difficult, or maybe you might have misunderstood something, or in something that I'm told once in a while is that there are parts of documentation I just don't understand. So could you provide some help on that? So how do you get help? I mean, first thing you can do is you can visit the MNE website, mne.tools, and click on tutorials in the navigation bar, and you get a plethora of tutorials that guide you through. Is somebody trying to say something, or is that just, okay, it's just background noise. And guides you through different tasks you typically need to do when working with MEG and EEG data, or even near infrared data. So that's the first thing you can do. After you've read through the documentation and you've pulled out all your hair, in the past, you would then probably send a message to the mailing list. And so I'm not sure, I don't know about you, but for me, these messages often looked like this, like with these weird warnings, external email and virus scanner, and I don't know what, which didn't seem too nice. So I never really used the mailing list because I found it a bit annoying. Another option that people chose is to post an issue on the GitHub issue tracker. However, that's not the best place to ask usage questions, because that is the space that developers typically use to keep track of bugs and to fix issues. But do not despair, we have something new, a shiny new forum. You can find it at mne.discourse.group, and it runs in your browser, and it's modern. It feels like 2021. You can subscribe to get email notifications for every new message. You can also limit that to individual topics or tags. So you can see here, oh, my mouse cursor disappeared again. Well, you can tag topics, and if you're only interested, let's say, in EEG, then you can get only the notifications for EEG if you want to. There's also direct messages. You can edit your questions. It's very easy to attach screenshots. Yeah, I think it's a pleasure to use, and if you haven't checked it out by now, do it. I encourage you to do it. Another thing, today is Monday, 3 days was it 3 days ago? Last Friday was 3 days ago. We recently started that, is MNE office hours. Last Friday at 4 UTC, that was at 5 p.m. In Paris time, we had the first MNE Python office hours on Discord. Discord is a chat software, maybe slightly similar to Zoom, or maybe like a bit like a hybrid of Zoom and Slack, if you will. And users can just come by and ask questions, and they can actually talk in a video call with the developers. And it's super convenient and can be of big advantage to go there, because you can also do screen share. We can do some kind of remote support, and I think it's a great addition to the forum. And just yeah, it just enriches the interaction, or the possibility of interactions between developers and users, or even users and users. The idea is to have this bi-weekly, every Friday. Yeah, like I said, we only had one office hour so far. We will have to see how it goes. Maybe we adjust the schedule. Also open for any kind of suggestions, feedback. Maybe you would love to attend, but the time doesn't suit you. Just pop us a mail or a post to the Shiny New Forum so we can talk about this and maybe can do some adjustments. The last thing I would like to address is actually a bit of a pain point, unfortunately. There's this great software, FreeSurfer, which we use for parcellation of the MR scans, and it is required to have this software installed and working if you want to do source localization. Now, the latest version of FreeSurfer, FreeSurfer 7, actually unfortunately removed two functions that MNE needs to work. They have meanwhile added it back in, but there hasn't been a new release that has these two functions. So for now, you are stuck with FreeSurfer 6. So do not install FreeSurfer 7. Stick with FreeSurfer 6. Well, but still, if you're a Windows user, it's painful, because FreeSurfer only works on Unix systems, Mac OS, Linux. So currently there is no easy way to do source localization on a Windows system. However, I've been looking into that, and there might be a way, and now I'm putting pressure on myself because I'm making a promise, because I believe it would be not too difficult to create a Docker container of FreeSurfer. Actually, there already exists one, and make MNE interact with a containerized version of FreeSurfer. So the idea would be that you only need to install Docker, which is essentially a lightweight virtual environment management tool. You just need to install Docker, and then MNE can use FreeSurfer, which runs in an isolated Docker container. And that would work across all platforms, Windows, Mac OS, Linux, and you wouldn't have to fight with the FreeSurfer installations anymore. Another thing we've been looking into is parallelization. We want to go large scale. If you have, say, hundreds of data sets, you probably don't want to process them locally. You want to use massive computing resources, maybe even from an Amazon data center or something. Currently, this is not convenient to do with MNE, but we started some work. We're looking into that, and hopefully within the next few months, there will be a possibility to very easily tell MNE, hey, I've got an account with Amazon. Please register 500 CPUs for me and 3 terabytes of RAM and process my data on these machines remotely. No ETA so far, but the next, I think the next few months, I think we can make this promise, but no specific ETA. Oh yeah, and one last thing, almost forgot about that. So Apple, some of you may follow the developments in the Apple universe, and they have recently released a new chip. It's called the M1. They call it small chip, giant leap, which is a bold statement. It's a very energy efficient processor that supposedly delivers good performance nevertheless. And Dennis Engelmann, a long-term MNE developer, got a notebook with a chip like that. Actually, got a MacBook Air, which is the low-end version of the Apple laptop spectrum. And he ran some benchmarks. And he essentially compared performance of typical MNE functions running on that computer to running the same functions on a much more powerful MacBook Pro. And on the x-axis here, you can see the time required to finish certain operations. And the red points, the red circles, show how long the new M1 processor took for him. And you can see they're constantly left of the blue circles, which are the powerful MacBook Pro machine that he had in stock and had used for the past few years. Interestingly, the yellow circles indicate an emulation of the Intel CPU. So this M1 chip is an entirely new architecture, but it can act as if it were an Intel CPU. It would do some emulation, and even the emulation is faster than the native i7 processor on a not so old PowerBook. So that is kind of amazing. So with that, I would like to conclude. I would like to thank you. I would like to thank all projects, all collaborators that MNE could and can rely on. And I'm happy to take your questions. Thank you.
So Florent, shall I also do the post-doc animation, or?
If you will.
Okay, so thank you very much, Richard, for the presentation. I don't know if there's any question from the audience, or it can also be, I think, a live discussion. And we can continue offline if you want. You can type your questions if you want.
Oh, I can see there's. Should I stop the screen share?
There's a few messages, but I'm not sure there are questions.
Okay.
There was a remark from Dennis about FreeSurfer that should nowadays work on Windows using the Linux subsystem. I don't know if you know anything about this.
Come again? Sorry, I was reading and not listening to what you said.
Dennis suggested that FreeSurfer could run on Windows using the Linux subsystem.
Yes, that's true. That is true. But I think it's so. I haven't tried that yet, but I talked to some co-workers, colleagues of mine that tried to do that, and they said it was still painful. So they felt that it's still too difficult for the average user. And I think using something like Docker would largely reduce that pain point. I'm going to stop the share so I can see you. Is there any more questions? Callback logic. Yes. So there are actually callbacks implemented. This is how when you do the 3D visualization, you can click on any point of the brain, and it would then display the trace right at the bottom of the screen. I'm not sure if you remember. Otherwise I can also show you again. So these callbacks do exist. Whether you can hook into them as a user, that I'm not sure about. Alex, do you know whether that's possible?
If I may jump in. Yeah, thanks, Richard, for the presentation. So if I may jump in, yes, that was my question. Can you hook these callbacks? Like, it would be super nice to just click on a voxel, and maybe the whole analysis in your notebook would change in accordance with the voxel that you just selected.
It's not exposed. You cannot pass a callable, but we could. And we have the same request for raw data to be able, for example, to fit a single dipole on a specific time point that you handpick. For example, for epilepsy needs, where you would do a dipole fit on a spike. I guess I don't think this is hard to do. Is nobody really pushed for it or took the stab at starting to do it, so that's why it doesn't exist. But there's no decision that we don't want to do this. It's really a matter of who wants and who has the energy to do this.
I can ask a question. First of all, this was a great talk, very, very exciting and beautiful software. We all use it. But I had more a question about the scientific approaches and advances. I am one of the people who are a little bit disappointed by minimal norm estimate as an estimate of sources for cognitive functions, at least. Sometimes we get very widespread activation that doesn't seem to be very realistic. Like, it's auditory, but it's going all the way to the middle temporal gyrus or something like that. So I wonder if there are important advances in narrowing down the actual sources. And maybe also a question to Alexandre. A year ago, you showed us this incredible optimal transport way of aligning subjects. Is this available now in MNE? And what is the progress with focusing the sources with this tool?
So Richard, if I may.
Oh yeah. I mean, you can take it entirely, I think, because you're.
Okay.
Yeah.
So the first aspect on the question, in MNE, you have you have a lot of source imaging techniques that are being implemented, probably much more than in other competing software. I don't know if there's been a lot of efforts for people to bite the bullet to start something new, but I know that some teams have used this kind of sparse solvers to avoid these big blurs that you're referring to. And so if you want to give it a try, I'd be happy to help and also hear feedback and complain if it doesn't work.
So sparse priors are available in MNE, right?
Yeah, there's been, I mean, it's one of the few things that I added from my personal research to MNE. And so it's been there for quite some years. And some groups have published with it, but not in Neurospin. And related to the other question, Isham Janati, who is my student working on this group approach, has a package called Group MNE that is hosted on his own GitHub. But for this, I don't know anyone but Isham who has tried to use it. But if you want to beta test it, then we're happy to provide the support.
That would be more for Fosca, yeah. But well, thank you very much. It's I think this is still a problem with this sort of. It's not MNE specific, but I think there is also, because exactly as you say, there are multiple methods to do the sources. What I see in some circles is a sort of double dipping, or p-hacking in a sense, where you search for the best source reconstruction that suits your expectations the most. That could be a little bit dangerous. So I think it might be nice to have an official recommendation for the best parameters and the best tools.
That's a tricky question. Because the problem that the fact that the problem is ill-posed makes also the answer not really quantitative, and very much based on simulations, where people sometimes do not believe in simulations, and so it's a tricky thing.
So we agree. Thank you.
Yeah. So if I just may add something before, unless there's any other question. No. So really one take-home message, I think Richard really clearly tried to highlight this point, is that we try to have a very open discussion. So I know some of you are asking their questions on the forum and publicly. And I think it's very important to share the knowledge beyond the walls of Neurospin as the way as other people are doing the same thing outside. And I'm really trying to, I would say, stress and insist that we find bugs everywhere and we try to fix them wherever we have the skill sets. And so please interact on issues publicly. And that also makes it a possibility for having people on the other side of the world to fix your problem, which sometimes happens. So do it in the open, and hopefully we'll fix our issues. And if people in UW need to fix Sophie's problem, so in Seattle, then that's great. And sometimes it goes the opposite. And I think it's a very, very good way to collectively progress, because we still find difficulties processing MEG in G after inventing MEG for 50 years. And so we still have some progress to go, and I think we should do it together.
Yeah, I would like to tap into that as well. So if you find yourself constantly in need of using some weird workaround that feels awkward, or you think there is a bug and you specifically work around that, it's always a good idea to report that, because once this has been addressed, we call it upstream, like in the MNE code directly, you can stop worrying about that. If you always have these workarounds only locally and update to the next MNE version, the workarounds might break. But as soon as fixes have been implemented upstream and then it breaks, you can blame the developers. Hey, you screwed it up. It used to work in the previous version. There is a bug. It doesn't work anymore. So it's not on you anymore. And that can actually be very helpful and a time saver. Yeah.
One more question. I may have missed it in your talk because I was distracted by a phone call, but is there a gallery of the best pictures out of MNE? Because that could be very inspiring sometimes, just to see the existence of a particular way of plotting.
So for the MNE study template, we have this example gallery, which should probably be improved, because currently it's essentially a bunch of buttons that lead to HTML reports, which then have figures in them. So it's not exactly what you're looking for. There are pictures in the tutorials. So when you click on the tutorial link in the navigation bar on the MNE website, you get these thumbnails of some hopefully representative figures that are generated in that respective tutorial. But I don't think there is these are the most amazing pictures ever created with MNE gallery. That could be a great idea. Could be a great idea.
Cool,
yeah.
Yeah, can I ask a question too? So actually, before the question, I would like to stress that Richard accepted to give the talk on a short notice due to a change in the speaker. So thank you a lot, Richard, for that. My question is, could you give us a rough idea of who the MNE users are? How big is the community? Are they scattered around the globe or clustered in specific places?
I would like to deflect this question to Alex, because I think he knows the numbers better than I do.
I think it's very distributed in terms of developers. I mean, of course, there's two full-time engineers paid by INRIA and ANR hosted at INRIA, but you also have developers that are paid at MGH in the Martinos. Other people are at University of Washington in Seattle. So these are people paid on grants out internationally to support MNE. Then you have people contributed also historically a lot in Alto. So you have distributed contributors over the world. And in terms of users, so I can give you stats on number of page views on the website, but I can also tell you that the MNE paper was cited something like maybe 250 times last year. So people do science and publish science using MNE, which is I would say a measurable outcome.
Okay, and I also have a scientific question. So I tried a couple of times functional connectivity analysis, inconclusively. And two difficulties there are that, well, it takes time to compute, and that's also a bit difficult to visualize. So do you have things in MNE for that?
That's a long debate about what's the right way of doing functional connectivity on MEG and EEG, besides doing what the previous paper has done. How do you set the parameters? How do you do stats on this? I mean, the MNE, so MNE was funded by NIH like 7 or 8 years ago. Was one of the aims was connectivity. So we added this function, basically implementing everything that existed out there. So you have like 7 or 8 methods implemented, and people come to me every time. So which one do I use? And my answer is I don't know. And so honestly, I've never really published myself doing this. I know there's a strong interest in using this. And I think Jan Matthijs from Fieldtrip has the same concerns about functional connectivity on MEG. There's a lot of open questions about, I mean, Stan was mentioning double dipping, but I think connectivity with the list of techniques that exist, and how you filter, you choose your filters, how do you set your number of cycles, all these things, they create a number of possibilities, which is huge. And I think the power envelope approach, which has been successfully reused and published across studies, seems to be quite reliable. But was added more recently. So like just to repeat, the power envelope correlation approach is quite stable and replicable across labs and studies. The ones based on like bivariate spectral techniques are more skeptical. But this is just my personal, I would say, maybe I've never really used it myself, so it's just maybe a strong prior.
If I can quickly jump in,
yeah.
Daria La Roca, with whom we worked on functional connectivity, and with Philippe Siusiu on this sort of data, when we started doing functional connectivity with MEG, she actually benchmarked a few methods to try and compare their reliability and the stability. And it seemed that the WPLI was the most robust one. So we went with this one on different parameters. So I don't know, Denis was part of it. I don't know if he's here as well.
He used to
He's
be
here, but he's muted.
Left already.
I'm here,
But
yeah, I'm here.
Denis and Daria had worked on this. Oh, he's there.
Yes.
Do you remember, Denis, if she ever published that part, or she just kept it for?
No, I think it motivated the choice for the neuroimage paper, but I think these benchmarks were never published. But I also agree with what Alex has said, that it's really difficult. And it depends, of course, whether you just look at resting state data and then you look at these power envelopes, or whether you use connectivity in event-related task setting. But yeah, and then I think there's this other thing that many people in the clinical setting or in the EEG setting, they really want to analyze connectivity. And I think this is really difficult without actually performing source localization for different reasons. So my suspicion would be that if you do sensor space connectivity, you will most of the time measure something that is related to the field spread and not really to a neuronal interaction. And yeah, but it's a continued discussion. It doesn't mean that this is not an effort that should be pursued.
I think one way to answer this question is try to use the same types of tool across studies and see what is like stable and consistent and what is reliable, and then that allows you to make some informed decision. Maybe what we're trying to do is the standardizing of the pipeline. If we add some connectivity step in the pipeline and we can run this connectivity across 10 data sets and see that it tends to provide interesting results, that could be a way to answer what you're asking.
That's a good idea.
There has actually been a paper a while ago, I think from the Oxford group, if I'm not wrong, on retest reliability of different connectivity measures. It was a small technical note in neuroimage, I don't find the reference right now, but I'm searching it right now. I can put it in the group chat here.
Any more questions, suggestions, criticism?
All right. See you on GitHub, discourse.